Okay, welcome to part 2 of video series 2 for mastering probability and statistics in Python. In the previous part of the video series, we discussed basically the link of conditional probability and machine learning. In this part, we are going to discuss the random variables in the real data sets. So we will explore some of maybe a couple of real data sets in Python, and I will show you the notion of random variables that are there and how to identify the random variables and what to do, what not to do with the random variables to build data science models in real data sets. So let's dive into the random variables for real data sets. We have discussed these random variables a lot, particularly discrete random variables, the random variables that has countable values. I can discuss theory more. I can discuss more about random variables, discrete random variables, a lot of derivations, a lot of examples and stuff. But I just feel feasible or necessary just to show you some real data sets and build a connection of these random variables on real data sets. And particularly what kind of random variables are there in real data sets, particularly in data science and machine learning, what kind of data sets are there? What are the notions of random variables are there in the data sets, and what we really do in those kind of data sets. So let's go to Python and see some of the built-in data sets and get a look and feel of what random variable is in real data sets and what are the tasks that are associated with, what are the machine learning tasks and what those tasks have to do with these concepts that we just studied so far. So let's go to the let's go back to Jupyter Notebook. So let's import pandas as PD, the dataset library for handling different kind of data sets. Let's import, for example, we already have SNS with us, so let's import some data. Let's say let's import iris data. So iris data from SNS dot load dataset iris. Let's import that data and see what that data looks like. So let's just see the first 5 records. Here you can see the data has different kind of attributes. We can call them attributes. So we can call them attributes like this sepal length is an attribute, sepal width is an attribute, petal length is an attribute, petal width is an attribute, and the category is this attribute species. The different kind of categories, let's see the different kind of categories. So let's say iris dot species dot unique. So the different kind of so there are 3 different kind of categories: setosa, versicular, and virginica. These are 3 different. So the total number of different values for this particular attribute is 3 values. This particular attribute is continuous. It can have several values. I mean 5.1, 5.1223 or something like so. This is sepal width and all that stuff. In machine learning, we call these attributes as attributes or features, but these are really the random variables. One random variable is sepal length, one random variable is sepal width, one random variable is petal length, one random variable is petal width, and one random variable is the type species. For example, if the next person walks in, and let's say we have certain machinery or extractors that can measure sepal lengths and sepal widths. Let's say we have tool or machinery that can that machinery can measure these kind of attributes: sepal length, sepal width, length, petal width, and let's say we can define the species as well. There is a machinery that can specify that as well. Let's say the new person that will come in, what will be the sepal length of that person? Well, that's random. It can be any number. What will be the sepal width? That's again random. What will be the petal width length? Random. What will be the petal width? Random. What will be the category of that person? We do not know. So all these are random variables. And one goal might be to come up with a distribution that says, okay, what's the distribution? What's the probability of species? What's the probability that species is setosa given the values of random variables? For example, let me call the sepal length as random variable x1 that has certain value. Let me call the random variable x2 as the sepal width. Let's say that has a certain value. X3 is, let's say, petal length that has a certain value. X4 is, let's say, the petal width. That's a random variable that has a value. So we might be interested in this particular distribution. If we, for example, specify the random variable species as y, we really are interested in the probability mass function of y given these four random variables. And we are calling this as probability mass function because the total number of values that this y can take are just 3. Y can take values between, let's say setosa is coded as 0, versicular that is coded as 1, let's say virginica, let's say that is coded as 2. So the total different values that this y can take, setosa has a code 0, let's say, as we can see here, setosa, versicular, and virginica, they have different codes. Let's give them different codes 0, 1, and 2. So this is basically the probability mass function because y is discrete. But what about these x1, x2, x3, x4? Are they discrete? What about the joint distribution? I mean, x1 is maybe a completely different random variable with different distribution. This x2 is a random variable maybe with different distribution. x3 is a random variable individually with this different distribution. x4 is a random variable with a completely different distribution. What about when they play together, their joint distribution? What do we mean by joint distribution? What we have to do with multiple random variables? We need to know that. But at the end of the day, if somehow, one way or the other, if somehow we can specify this PMF, this probability mass function, then if this probability mass function is specified somehow, maybe going through data, maybe applying certain statistics of the data that we will see in detail in the upcoming videos. But right now, I just want to give you a look and feel that this is a real data. These are random variables, and we are interested in this particular distribution. Where this is a random variable, that's a random variable, that's a random variable, that's a random variable. And we are interested in if you want to do this classification, if you want to, for example, if our goal is that given the sepal length, and given the sepal width, given the petal length, given the petal width, can we determine the category? Can we determine the species? Maybe we have machinery or sometimes called a feature extractor that can extract these kind of values automatically. Then our goal is, given these values, can we detect species? Well, that problem is exactly this. Can we model this PMF? If we can model this PMF from the data or using certain tools, at the end of the day, if we can model this PMF, where x1 is a random variable representing the sepal length, this is sepal width, this is petal length, petal width. If we can model this distribution, the PMF, then we have our problem solved, and that is a classification problem. But here you can see these random variables, sepal length, sepal width, petal length, petal width, they don't look like to be discrete. For example, sepal length might be 5.1, it might be 5.001, it might be 5.111332224. And sepal length can assume any value, for example, between 4.9 and 5.1. Any value in between might be a valid value. So it is no longer discrete. The total number of values that a sepal length can assume is not countable. These are continuous, and there are so many continuous. All these are continuous. There may be a mix of continuous and discrete values. For example, let's load another data set. For example, a Titanic data set. T is SNS dot load data set. Let's say Titanic. If you see that data set, for example, there may be a mixture of values. Here, one random variable is survived. That's a Bernoulli random variable, because here whether a person survives or not. So the values are 0 and 1. That's a Bernoulli random variable. If you want to see T dot survived dot unique, so if you see that the only unique values are 0 and 1. So this random variable, whether the next person will survive or not, that's a Bernoulli random variable. Then there are passenger class. This P class, that might be, let's see, T dot P class dot unique. That might be, that's again a discrete random variable with just 3 values. This gender, that's a discrete random variable. Age, that I guess is a discrete random variable. Siblings, that's a discrete random variable. Parts, that it's a discrete random variable. So several random variables are discrete, but here this fare doesn't look like a discrete random variable. It looks like a continuous random variable. Then we can have a mixture of discrete and continuous random variables, and if our goal is to predict the survival given the rest, so if that is our variable of interest, which is Bernoulli, and we want to basically predict the survival rate given the rest of the values, given the rest of the random variables. That is basically a classification problem, and in this particular paradigm, it looks like if y is if y, for example, if y represents the survival, then our goal is to build a PMF or probability model of y given x1, x2, x3, x4, x5, and so on. And these are several random variables. And some of them are discrete, some of them are continuous. How we are going to model a PMF with a mixture of discrete and continuous random variables, and more precisely, there are multiple random variables. Each one individually can have a different probability distribution. And first of all, what is the way to define distribution for a continuous random variable? We have to see that. Then we might be able to mix the discrete random variable with continuous random variables and stuff like so. So again, at the end of the day, if we want to solve the classification problem for this, for example, Titanic data set, we have to model this probability distribution, which is a conditional probability distribution. We have to model that somehow from data using certain techniques that we will learn in the upcoming videos as well. But I'm just giving you a look and feel of what random variables they look like. And it is not always required to have a very good description of what a random variable is. Sometimes the real data just arrives and we are just interested in a one random variable, whatever its description is, based on the rest of the random variables. We need not to know, these names need not to be very descriptive and telling what the numbers where they came from and stuff like so. Sometimes the data might just be written in these names that may be very unfamiliar to you, and then but your goal is to go through the data, somehow come up with a probability distribution, which sometimes we call as let the data talk. Data will define, data will drive all the distribution and all that stuff. So for example, let me give you an example. Let me give you an example of another file data set that is located there. Let's say I have this data file here. Yeah, so that's a bias correction data set. Let me just copy the path of it. Control C. Let me just open up and see if we can read that file. pd.read CSV, or let's see if you can read it properly. B.shape. Yeah, we read it. So now if you see B.head, so here you have a lot of random variables. Station, date, present temperature max, that's a temperature data, present temperature minimum, that is LD, APS, RH min, whatever that means, it has these values. I need not to know what this represent. If I know, that might be better, but even if I don't know, I will see the data and come up with the distribution. That all I know is this is some random variable, and I have to deal with it. That's another random variable. There are so many random variables here, actually 25 of those. And what if I'm interested in given all these, given the values of all these random variables, what if I'm interested in, given all the random variables, I want to predict the maximum temperature for the next day and the minimum temperature for the next day. So given a lot of features, the values of a lot of random variables, I want to predict the maximum temperature for the next day and maximum temperature for minimum temperature for the next day. Here you see what you want to predict is also continuous. It is no longer discrete. So which means if you go back to your page again, which means you're going to build a probability model. You want to predict the probability. You want to build a probability model for y, where y may be the next temperature, the temperature of the next day, maximum temperature of the next day, given a lot of information, given the values of a lot of other random variables. But here, this y is no longer discrete, so you cannot call this probability model as a PMF, because PMF is referred to the probability model or probability mass function for discrete random variables. If this y is no longer discrete, how can we model the distribution of that? And it can appear, I mean, in classification problems, for example, this particular variable is always discrete, so it is okay to just go with PMF. But in regression problems where we want to predict a continuous value, which may not assume countable values, this random variable will not be discrete, and how to handle these non-discrete variables. This is not just theoretical part. I mean, in all regression problems, the variable of interest, sometimes called the dependent variable or the dependent feature on the rest, that is no longer discrete. So how to model this distribution? And by the way, if we want to predict the value, the regression value, the value of this variable, should we go for the probability distribution for that, and check what's the probability that y will take value 1, what's the probability that y will take value 1.31, and so on. Should we list all the probability values and pick the maximum one? Is that true? Or should we do something else? Maybe we calculate the expected value of x, or average that y can take given these situations. Yeah, I mean, there are a lot of things. We have just covered Bernoulli, I mean, geometric, binomial, and stuff like so. And you might be thinking that where they play the role. Well, the real data set, when you see it, all the attributes, whether you are doing a classification problem or a regression problem in machine learning, you are given the values of a lot of random variables, and you are going to predict a particular random variable for that. And you have to build a probability model from the data. So this data, the data is given to you, sometimes called the training data, and using that data, somehow you have to build this model. And building this model from data is not an easy task. It's a really tricky task, and sometimes really hard. And that's what you want to do. So you need to know the random variables. What are these? Sometimes some of the values of the random variables, they are given, and you're interested in the rest. Consider, for example, again, that I also mentioned, this if in the face recognition problem, these random variables, they might be the intensity values of individual grid pixels, and this might be the identity of the person. Now, if the camera captures the image, the face image, then these values will be available because the camera supplies these values. But the camera doesn't know, I mean, nobody knows, given these values, what should be the identity of the person. That you have to predict. So in many cases, these feature extractors, they are available, and they supply the values that you need, that you want to condition on. But then the real goal is to predict this value. And to predict this value, you have to build a probability model. And to build a probability model, you need to go through a lot of data to build that model reliably. Yeah. So in this particular video, I built a lot of needs that are required. Number one, how to handle a continuous random variable. What if the random variable does not assume countable values? How to handle that? Number one, that's a problem. We have to see it. We don't know yet how to deal with that. Number two, what if there are more than one random variables with different distributions? Their individual distributions may be different, but what if they work in a joint fashion? So how to model joint distribution of several random variables, more than one random variables? Well, this joint distribution also have two cases. If all the random variables, they are continuous, and all of them, they are discrete. So we have to see that. And the third confusion is, what if there are, the third thing that we have to see is, what if these several random variables, they are mixed types. Some of them are discrete, some of them are continuous. Because at the end of the day, we are going to read the real data. The real data will be full of several continuous random variables, several discrete random variables. It might be a classification problem in which the target random variable will be discrete. It might be a regression problem in which the target random variable might be continuous also. So how to model joint distributions, how to model conditional distributions, given several random variables, how to model joint distributions, how to apply a Bayes rule in this kind of situation when we have a lot of random variables, not just one. Yeah, so we have to answer all these questions to actually get juice of the data, to get the actual training from the data, to get the actual model from the data. So yeah, we have to go through continuous distributions, continuous random variables. We have to go through multiple random variables. We have to build the joint distribution or the joint probability models that involve multiple random variables, mixed random variables. And then we will be able to go and look into the data, and we'll be able to build those models using statistics. Yeah, so we have to do that. So a lot of things are coming. Hope to see you in the next video. In this video, we discussed the random variables in real data sets by actually showing you the random variables on a couple of data sets in Python. In the next video, part 3 of the same series, we are going to discuss a continuous random variable, particularly the Gaussian random variable. And we will be discussing that random variable, we'll be plotting that random variable, we will be seeing its parameters and what is the impact of the parameter over the continuous density of the Gaussian random variable. So hope to see you in the next part.